we now give the precise statement of the strong Markov property for continuous time Markov processes. Our state space S will be a separable metric space. We'll have a filtered probability space on which the process is defined, and our Markov transition semigroup, this time stated in terms of the transition operators defined on the bounded measurable functions on S. We'll take a time homogeneous Markov process having that semigroup as its Markov transition operators, and we will assume that it is a at least right continuous path process. Its paths live either in the right continuous functions or the continuous functions on the positive time interval. There's one technical assumption that we will need, which is the following assumption about the Markov transition semigroup. We assume that there exists a multiplicative system of functions inside the continuous bounded functions on the state space that generates the full Borel sigma field of that state space and is preserved by the Markov transition operator for each time. Under those assumptions, we have the following strong Markov property. If we take any bounded measurable function on the path space, measurable once again with respect to the cylinder sigma field, and any stopping time, then if we take the shifted process x at tau plus, take that function of it and take the conditional expectation given the stopped sigma field f tau, that is the same as taking the expectation of the process started at 0 in initial state x, where x is evaluated at the stopped process x tau. And that holds almost surely with respect to whatever the initial distribution of x was, on the event that tau takes finite values. Now we can also make a similar statement if we only know that tau is an optional time. If tau is an optional time, then precisely the same statement holds, provided that we condition here on the larger sigma field f tau plus. Now, of course, if the filtration is right continuous, then stopping times and optional times are the same thing, and indeed f tau plus and f tau will be the same, so those are the same statement. But we'll go ahead and be careful and focus actually on this putatively weaker statement. In fact, it's a stronger statement because this implies this one. The way to see that is as follows. Suppose that we only know this holds true for optional times. Well, any stopping time is an optional time, and so that means that this will hold true for our stopping time tau. We'd like to be able to condition on this smaller sigma field and still get the same result, and we can do that because if we then use the Tower property for conditional expectation, well, that will equal the conditional expectation of this onto f tau as well. But as we proved in lecture 56.3, in the case where tau is a stopping time, x tau is f tau measurable. And so since this is a function of x tau, conditioning on f tau won't change its value, which means that we will get this value again. So that shows that this statement here is enough to prove this one, and so we will focus our attention on proving that statement in the proof. But before we go into the proof of this, let's see some examples of how to apply it, and in particular, where these technical conditions actually apply. To start, let's look at all of the processes that we spent the middle of this course studying. Continuous time Markov chains. That is, Markov processes where the state space is a countable discrete set. And indeed, we focused a great deal of attention on the very regular case where the Markov semigroup is operator norm continuous. That is, that as t goes to 0, Qt converges an operator norm to the identity operator. As we saw, that's equivalent to the process having a bounded generator, A, and so these are sometimes called bounded rate continuous time Markov chains. For those processes, we have the jump hold description that we proved in lecture 42.1. That is to say that the way that the process operates is to have an underlying discrete time, discrete state space Markov chain that it jumps between, and then at each state there's an exponential clock with rate determined by what state you're at that goes off at some positive time, at which time you jump to the next state according to the discrete Markov chain. In particular, that means that the paths of this process are right continuous. They're piecewise constant, staying in whatever state that we're in until that exponential clock goes off, and then we jump to the next state, and then we jump to the next state. Now, that description doesn't tell us all of the path properties, of course. It doesn't tell us what the value of the process is at the jump times. But as we can easily see, just like in the case of the Poisson process, which is a special case, we can choose a version of this process which is right continuous with left limits. That is, just by choosing the value at each jump to be the new state that we're in the next positive time interval. So in particular, that means that these processes have right continuous versions, and we can realize their laws as measures on right continuous path space. Now, all of those processes are, of course, Markov processes. So the question is, do they all have the strong Markov property? And by the theorem, as we just stated it, they will have the strong Markov property, provided that their Markov transition semigroups satisfy this technical condition, that there's a multiplicative subsystem of the continuous bounded functions on the state space, which is preserved for each time by the transition operator. But our state space is discrete, and that means that all functions are continuous. So actually, we just need a multiplicative subsystem of all the bounded functions. And actually, we can just take it to be all the bounded functions. Because, as we proved in lecture 34.1, Markov transition operators are always LP contractions for every p, including infinity. So that shows us that if I take qt of any function in the continuous bounded functions on S, which as we just noted is the same thing as the bounded functions on S, well, this shows that qt applied to a bounded function produces a bounded function with the same or smaller bound. So this is indeed contained in the bounded functions, which is the continuous bounded functions. And of course, the space of all bounded or continuous bounded functions is a multiplicative system. It's closed under a pointwise product. And so therefore we can take that M equal to that space, and we get the technical conditions are met. So according to the theorem, all of those processes will have the strong Markov property. For a concrete example, let's again think about the Poisson process. There in lecture 39.2, we explicitly calculated the transition operator. This is defined on bounded functions on the state space, which is the natural numbers here. And qt was defined exactly like this. Is this nice sum, and we can just explicitly compute here if we don't believe or remember the general theorem that I'm stating here, that qtf at any point x, well, that taking the triangle inequality through that sum is less than or equal to the sum n going from 0 up to infinity lambda t to the n over n factorial e to the minus lambda t times f at x plus n in absolute value. But of course, this is just less than or equal to the sup norm of f, so we can pull that outside the sum. We get that this is that sup norm times the sum n going from 0 up to infinity of lambda t to the n over n factorial e to the minus lambda t. But of course, taking this outside as well, this sum is equal to e to the lambda t, and so that's just equal to the sup norm of f. So the long and the short of that is that all bounded rate continuous time Markov chains have the strong Markov property. Now, how about the continuous time Markov process that we've been spending most of our time studying lately, Brownian motion? And let's be general here, Brownian motion on Rd for any finite d. Well, here the state space is Sd, equipped with its usual Euclidean metric structure. And as we showed in lecture 38.1, the transition operator of this pre-Brownian motion even is this nice convolution operator here. Qt of f is f convolved with the Gaussian density. That is, the density of a normal random variable centered and of covariance equal constantly to t times the identity matrix. Another way to write that same thing, utilizing the connection between convolution and independence, is to say if we choose a standard normal random vector z, that is, all of its components are independent standard normal random variables, then this is the probability density of the random vector root t z. And so that means by the change of variables theorem that this convolution value at any point x, which is the integral of f at x minus y gamma t of y dy, well, that's just equal to the expected value of f at x minus root t z. But z is symmetric. It has the same distribution as minus z. So for convenience, let's actually change that to a plus sign. That won't change anything. Now that's really convenient for what we need to show here, because it follows from this quite easily that this Markov transition operator preserves the space of bounded functions, at least. We already knew that, but let's just check it again. For any x, if we take the absolute value of qt f at x, that's equal to the absolute value of this, but by the triangle inequality, that's less than or equal to the expected value of the absolute value of f at x plus root tz. And that inside is less than or equal to the sup norm of f, of course, no matter what x is or what the values of root tz are. And by the monotonicity of expectation, if this random variable is less than this constant random variable, then the expected value is less than or equal to the expected value of this, which is just that sup norm. So again, we have that the transition operator for Brownian motion preserves the space of bounded functions. Well, what about continuous functions? Those are no longer just all bounded functions in this continuous setting, but the same realization here we've made will allow us to prove that as well. If I take a sequence of points xn in Rd that converge to some point x in Rd, then for any continuous bounded function on Rd, if I look at qt of f at the point xn, well, by our realization up above of qt, that's the expected value of f at xn plus root t times z. Now inside here, f of xn plus root t times z, that converges almost surely to f at x plus root t times z. And that's just because f is continuous, and xn plus whatever this random point is converges to x plus that random point. We also have that integrand inside there is uniformly bounded by the sup norm of f. And therefore, by the dominated convergence theorem, the expected value converges to the expected value of f at x plus root t z, which is qt f at x. So what that says is that if we take M to be the full multiplicative system of continuous bounded functions on Rd, then Qt preserves M. Qt preserves the bounded continuous functions. And so, since we're working with Brownian motion, which is the continuous version of this pre-Brownian motion process, by the conditions that we set out for the theorem, we now know that Brownian motion has the strong Markov property, which will be a very effective tool we'll use to deduce finer properties of the Brownian motion. So we should now turn to filling in the details of that proof, but let's do one more thing before we do that to convince ourselves that the theorem is stated in a natural way. Remember, the strong Markov property as we've stated it requires that we take the law of the process to be defined on the sigma field generated by the projections, the cylinder sigma field. Now, we might think that that is a particularly small sigma field and isn't large enough to detect the kinds of properties that we want to know about the laws of these processes. In fact, at least in the continuous path case, that sigma field is as large as we could possibly want. We've alluded to this fact before, but I think it's about time that we prove it. So here is the result. If t is a fixed finite positive time, and S is a separable metric space, let's denote by omega t the space of continuous S-valued paths on the interval from 0 up to t, and we'll turn that into its own separable metric space using the sup norm over that compact time interval. That is a complete separable normed space, a separable Banach space, if you will, owing to the fact that T is finite. That's important here. If we allowed the paths to be defined on the whole positive real line, then these norms could be infinite. But on a compact time interval, this is a Banach space. Then, in fact, the cylinder sigma field generated by those projections is exactly equal to the full Borel sigma field over this normed space. And so we're realizing the laws of these path-valued random variables, these stochastic processes, as Borel random variables, as we have throughout this entire course for all random variables. Just to keep our eye on the ball, so to speak, remember that the Borel sigma field is the sigma field generated by open balls. That is, open balls in the path space. And of course, these projections here, pi t, those are just the maps from the path space into the state space, defined by pi t of omega is omega of t for each t. So let's prove this now. One of the containments is very straightforward. That is that this is contained in this. That's just because the projections are continuous maps. In fact, they're Lipschitz continuous. If I consider the map pi t from omega t into S, then that is Lip1 continuous, just because if I take the norm of pi t of a point minus pi t of another point, omega prime, those points are paths, remember? Well, by definition, that's the norm in S of omega of t minus omega prime of t. And no matter what t is, that's less than or equal to the sup norm of omega minus omega prime. Indeed, this is just defined to be the supremum over all of these for different t's, ranging from 0 up to capital T. So that exactly tells us, with constant 1 here, that pi t is Lip1, continuous. In particular, since it's continuous, it's also measurable between the Borel sigma fields. And so the sigma field generated by these continuous functions is certainly contained in the sigma field generated by all continuous functions, which is what this is. So for the converse direction, we want to show that this is actually contained in here. And to do that, let's just look at some balls in this space. It's going to be convenient to leverage the separability of this space, which we'll witness explicitly using the same kind of arguments we've seen now over and over. A continuous path is determined entirely by its values on any dense subset of the range. In particular, that means that the supremum of any path omega is equal to the supremum over just the rational times. Which is the same thing as the supremum of pi t of omega for t ranging through rational times. Therefore, if I take any base point omega naught, remember that's some particular continuous path, then if I look at the function on path space, f sub omega naught, which is a function of omega, just defined to be the sup norm distance between those two paths, well, since they're both continuous paths, that can be computed as the supremum over rational times of pi t of omega minus omega naught of t, if we like. And that is a supremum over a countable collection of cylinder measurable functions. These functions here, these are certainly cylinder measurable. Since the cylinder sigma field is the smallest sigma field with respect to which all of these are measurable, and of course we're doing measurable things to those in the range. Now, a countable supremum of measurable maps is a measurable map. So that says that f omega naught is measurable from the cylinder sigma field into the Borel sigma field on the real line. But in the path space, omega t, the ball of radius r centered at omega naught is just the set of all points in omega t, for which that function, f omega naught of omega, is less than r. In other words, it's the preimage under this measurable map f omega naught of the interval, say, from minus infinity up to r. Now this is a Borel set, and that means that this preimage is therefore a cylinder set. So every open ball in this Banach space is a cylinder set. And since this space is separable, every open set is a countable union of open balls, which means that every open set is a countable union of cylinder sets, which means that every open set is a cylinder set. That is to say, since the Borel sigma field is generated by open sets, it follows that the Borel sigma field is contained in the cylinder sigma field. And so this cylinder sigma field is not too small. It's the same kind of sigma field, the Borel sigma field, that we've been working with all along. And that finally sets us on the path to the proof of the strong Markov property.